Welcome back to Sip and Talk. 2026 has barely started, and we are already facing maybe the biggest challenge we've ever had on the show.
Phew. We are recording. Good morning, good afternoon, good night, Sip and Talkers. No matter what time zone you're in, welcome back. Mm-hmm. I actually brought a fan with me today.
A fan?
Yes, because I have a feeling that by the end of this, both of our brains are going to be completely overheated and smoking. Today's topic wasn't my idea. It wasn't your idea. It was you, our amazing and, let's be honest, slightly crazy listeners who demanded this, the quantum mechanics all-in-one.
I pushed my glasses up when I saw this. I have to be honest. When I saw the message board just flooded with wave-particle duality and delayed choice and four-dimensional space, my first thought was, did everyone just have a collective nightmare about their final physics exam?
Right.
Because quantum mechanics is that one subject where if you think you get it, you definitely don't.
Yep. But challenge accepted. We're going to see whose brain starts smoking first. We are not reading from a textbook today. We are going on a full-on mental roller coaster. We're going to talk about why the world might not actually exist until you look at it.
Okay.
Why little birds can use quantum physics to navigate. And my favorite, whether dark matter is just a bug in the universe's source code. I mean, the list just goes on and on. You ready?
I think so.
If your logic is still feeling clear right now, don't worry. That just means we haven't started. Your turn to serve it up.
All right, if we're doing this, let's start at the very beginning. Let's start with the collapse of reality itself.
The first question that came in from listeners was a spicy one. It was, if I don't look at the moon, does the moon really exist?
And that question, which sounds almost like a riddle, takes us straight into this philosophical nightmare called the double slit experiment. It shows us that at the quantum scale, particles don't have a fixed state until we measure them. Before that, they exist as a wave, what did you call it? A probability distribution?
Right, it's not a single point. It's a cloud of maybes.
And this brings up the two big opposing views, right? You have the Copenhagen interpretation on one side.
The pro view, yeah. They say that's right. Before you look, the moon's exact location, its properties, they don't exist in a fixed way. It's all just probabilities.
But then you have Einstein on the other side.
The anti-view. He absolutely hated this stuff. I mean, his famous quote was, "I close my eyes and the moon is still there." He was convinced reality had to be real, whether we were looking or not.
So this is it's like having a scratch card with a 50% chance of winning.
Oh, that's a great analogy.
Before you scratch it, before you observe it, that little piece of cardboard is in a superposition. It is simultaneously worthless piece of paper and I'm quitting my job tomorrow.
Both states at once.
The moment you scratch it, the wave function collapses. Reality snaps into place. You're either rich or you're not.
And that's the core idea. Observation forces reality to pick a side.
I mean, I see this at work every day. When my boss is watching me, I am an elite, hyper-focused particle working on one single task. The second he turns his back, I collapse into a diffused wave, a lazy mess spread across 3 different browser tabs and my phone. My fate depends entirely on who's looking.
And that brings us to the biggest misconception, the one we really have to clear up. This idea of observation. It's not about, a conscious person looking. It's not your soul collapsing the universe.
Right. It's much more mundane, isn't it? And kind of violent.
It is violent.
Yeah.
To see something as tiny as an electron, you have to interact with it. You have to hit it with something, usually a photon of light, and that photon has to bounce off and go into your detector.
But for a little electron, getting hit by a photon isn't a gentle tap. It's like a person getting hit by a semi-truck.
Exactly. That physical interaction is what destroys the fragile quantum wave state. It's called decoherence. And the biggest observer isn't us.
It's the environment.
It's the environment itself. Air molecules bumping into things, heat, radiation. For anything big, like the moon, it's being constantly bombarded by photons from the sun, by cosmic rays. Its wave function is collapsing trillions of times a second.
So the moon is there when we're not looking because the rest of the universe is constantly looking for us.
That's the key. The environment forces it to have a definite location. But this whole idea that reality is probabilistic, it leads to some really strange places. Which brings us to Bell's theorem.
Yeah, the experiments that basically tried to settle the Einstein versus Copenhagen debate.
Right. And they essentially proved that if Einstein's hidden variables These secret instructions telling particles what to do did exist.
They would have to be non-local.
Meaning they'd have to communicate faster than the speed of light, which Einstein himself said was impossible. And experiments keep siding with the quantum view, with non-locality.
It's just so counterintuitive.
I have a real-life analogy for this one, too. Think of a situationship. That relationship exists in a superposition of friend and lover. It's a wave of pure possibility. But the moment one person performs an observation by asking the dreaded question, so, what are we?
The collapse.
Wave function collapses. It's forced into a single, definite state. Either lover or the very painful, very fixed state of, you're a really great person, but...
So asking the question is the violent physical interaction.
It is. It's an irreversible measurement. So now that we've established that reality is fuzzy and observation is a physical act, let's mess with time.
Great. Just what my brain needed. Let's pivot from the very small to the very, very big, to Einstein's world. We need to understand his theories of relativity before we can really break them.
Absolutely. Einstein gave us two incredible frameworks. First was special relativity. That's the one that deals with speed.
And the main takeaway there is that the speed of light is the absolute cosmic speed limit. Nothing goes faster.
Right. And because of that, weird things happen to space and time. The faster you move, the slower time passes for you relative to someone standing still. It's called time dilation.
And this isn't just a theory, this is real. It's why our GPS works.
It is. The GPS satellites are orbiting the Earth so fast that their internal clocks actually tick a little slower than ours down here.
And if engineers didn't correct for that tiny time difference every single day?
Your navigation would be off by, what, like 10 kilometers a day? Your phone would send you into a lake? We literally rely on time being flexible.
Okay, so that's speed. Then he gave us general relativity.
The big one. The one about gravity. And his idea was revolutionary. He said gravity isn't a force pulling things together.
Right, it's massive objects actually bending the fabric of space-time itself.
The classic analogy is the trampoline. You put a heavy bowling ball, that's the sun in the middle of a trampoline. It creates a curve, a dip.
And if you roll a little marble, that's the Earth nearby, it doesn't get pulled by the bowling ball. It just follows the curve in the fabric.
It's following the straightest possible path through a curved space. And this idea, this geometry of space-time, predicted everything from black holes to gravitational waves.
Which we finally detected in 2015. The sound of two black holes spiraling into each other. It was incredible.
A cosmic waltz. So, okay, we have the quantum world saying reality is a probability game. And we have relativity saying space and time are bendy. Now, let's combine them. Let's talk about the delayed choice experiment.
This is where my brain starts to melt. John Wheeler's thought experiment.
It's a complete headache. So in the normal double slit experiment, you decide beforehand if you're going to watch which slit the particle goes through.
Right. You set up your detector, and that choice determines if it acts like a particle or a wave.
Wheeler asked, what if we wait? What if we let the particle go way past the slits, past the point of no return, and then we decide whether to put a detector there or not?
And the result is insane.
It's insane. The choice we make in the present seems to retroactively determine what the particle did in the past. If we choose to measure its path after it's already passed, it turns out it behaved like a particle all along. If we don't, it behaved like a wave.
Okay, stop. That can't be right. How?
Well, they took this to a cosmic scale to really prove the point.
With gravitational lensing, right?
Yes. They look at a photon of light that had traveled for billions of years from a distant quasar. On its way to us, it passed a massive galaxy.
And the galaxy's gravity acts like a lens, bending space-time. So the photon has two possible paths it can take to get to us, around the left side of the galaxy or around the right side.
And that choice, left or right, was made billions of years ago. But what the experiment showed is that the choice of detector we use on Earth right now determines which path it took.
You're telling me a decision I make in this lab today changes the physical reality of an event that happened when the universe was like a toddler. That completely shatters the idea of cause and effect.
It really seems to. And it gets even weirder.
Of course it does.
It's called the quantum eraser experiment. In this version, you first get the path information. You force the particle to choose a slit, so it acts like a particle. You see the pattern on the screen. No interference, just two lines.
Okay, standard particle behavior.
But then, after the particle has already hit the screen, you can choose to erase that path information. You basically destroy the record of which slit it went through.
You erase the evidence.
You erase the evidence. And the moment you do, the pattern on the screen changes. The interference fringes. The wave pattern reappear.
No! That That's impossible. The particles already hit the screen.
It's as if the particles retroactively knew their path information would be erased, so they went back in time and decided to act like a wave instead.
So the past isn't set in stone. It's mutable. It only solidifies when we force it to.
It really looks that way. This has led to this really fascinating idea that a lot of people are talking about, this concept of lazy loading.
Like in a video game.
Exactly. In a video game, the computer doesn't render the entire world in high detail all at once. That would take too much processing power. It only renders the little piece of the map that you, the player, are currently looking at.
The rest of it is just a low-res blur.
Right. So what if the universe does the same thing? What if the exact path of that photon from billions of years ago was just a fuzzy probability until we, right now, force the universe to calculate and render that one specific detail?
The universe is just trying to save on its energy bill. That's both terrifying and somehow deeply practical.
It's an efficient universe. This nonlinear view of time is one of the craziest takeaways. The universe isn't a movie playing out frame by frame. It might be a single, interconnected block.
A block where the present can reach back and tweak the past. Okay, let's jump from time travel to instantaneous connection across space. Let's talk about entanglement.
Ah, yes, what Einstein called spooky action at a distance. He did not like this one either.
I'm sensing a pattern here.
He was a classical guy at heart.
Yeah.
So, quantum entanglement. The idea is you can link two particles together in a special way. Let's say you entangle their spin.
Spin is just a quantum property, like charge or mass. We can call it up or down.
Right. If you have an entangled pair, they're in an undefined state. But the moment you measure one and find that its spin is up,
you instantly know that its partner, no matter how far away it is, will have a spin of down.
Instantly. Faster than light. You could be on the other side of the lab or the other side of the universe. The connection is instantaneous.
Now, we should be clear, you can't use this to send a message, right? You can't, send Morse code this way. It doesn't violate relativity in that sense.
Correct. You can't control the outcome of your measurement, so you can't send information. But it does prove that reality is fundamentally non-local. Things are connected in ways our brains just aren't built to understand.
And this isn't just a thought experiment anymore. Yeah. The 2022 Nobel Prize in Physics went to the guys who proved this stuff is real.
It absolutely did. And that proof has kicked off a massive global quantum race. The US, China, the EU, everyone is pouring billions into this.
For what? What are the applications?
Two huge ones. First, quantum communication. Because of the way entanglement works, you can create perfectly secure, unhackable communication channels. And second, quantum computing.
Which uses these weird states of superposition and entanglement to do calculations that would take a normal computer millions of years.
Exactly. It's a whole new paradigm. It's like I order a super spicy bowl of ramen here in Silicon Valley.
Okay.
And the exact moment the bowl hits my table, my brother in Taipei gets a sudden, inexplicable stomachache. We are linked. That's entanglement.
I think I finally get it. So from the incredibly small, let's zoom all the way out again, to our home, the Milky Way galaxy, you said our mental picture of it is all wrong.
Totally wrong. We all picture this perfect, flat, spinning vinyl record, right?
Yeah, that beautiful spiral.
The reality is much messier. Recent data shows the disk of the Milky Way is actually warped and flared.
Warped and flared, like a Pringle, a potato chip.
That's a great way to think of it. The outer edges are bent up on one side and down on the other in this huge, slow wave, and it's flared because the disk gets thicker the farther out you go. It's not a neat, flat plane at all.
So what's causing this giant cosmic wobble?
It's gravity. Our galaxy is constantly in a gravitational dance, or maybe a tug-of-war, with its smaller satellite galaxies. They're pulling on us, distorting our shape, and the whole thing is embedded in this massive, invisible halo of dark matter, which isn't perfectly smooth.
So it's less like a majestic orchestra and more like a chaotic disco.
I love that. The stars in the center are spinning super fast like breakdancers, and the stars on the edge are swaying around like drunks who should have flown off into the parking lot ages ago.
But they're being held in place by the invisible bouncer.
By the invisible DJ, by dark matter. It's this messy, dynamic, fluid system.
While we're on these huge cosmic patterns, let's talk about something that connects all the scales. Fractals?
Yes, fractal geometry. It's this beautiful idea of self-similarity.
The classic example is that weird-looking Romanesco cauliflower.
Perfect example. If you break off one tiny little floret, you see that its shape, with all its little spirals, is an exact miniature version of the entire head.
A cosmic Russian doll. The pattern repeats at every scale.
And once you know to look for it, You see it absolutely everywhere. Lightning bolts, river deltas, the coastline of Britain, the branches of trees, the blood vessels in your lungs.
Even the neural networks in our brains.
They all follow these fractal patterns. And what that suggests is that the universe is really efficient. It uses very simple mathematical rules repeated over and over to build incredibly complex structures. It's nature's copy-paste function.
And it's not just pretty. This is used in computer graphics to create realistic landscapes, in weather forecasting, and even in analyzing the stock market.
The jagged, unpredictable ups and downs of the market follow a fractal pattern. The universe loves to repeat itself.
Okay, so let's bring it back from the cosmos to right here on Earth. Let's bring quantum mechanics into biology. The birds.
Yes. The quantum sixth sense. This is one of the most incredible discoveries in quantum biology. How do migratory birds fly thousands of miles over oceans with no GPS and arrive at the exact same spot every year?
They're navigating using the Earth's magnetic field, but that field is incredibly weak. How do they sense it?
They literally see it. Inside their eyes, they have a special protein called cryptochrome 4, or Cry4, and it's sensitive to blue light.
Okay, so a protein in their eye, what happens?
When a photon of blue light from the sun hits this protein, it creates something called a radical pair. Basically, two molecules that now have electrons that are quantumly entangled.
Entangled again, so their fates are linked.
Exactly. And this entangled state is extremely fragile and sensitive. So sensitive that the Earth's super weak magnetic field is enough to influence it. Depending on the angle of the magnetic field relative to the bird's head, it makes the electron spins flip in a slightly different way.
And that tiny change in quantum spin
leads to a different chemical reaction, which sends a different signal to the bird's brain. The end result is that the bird sees the magnetic field lines overlaid on its normal vision.
Like a natural heads-up display. Augmented reality. That's incredible.
It's proof that a warm, wet, messy biological system can actually use and maintain quantum effects for a real-world purpose.
Which leads us to the ultimate question. If a bird's brain can do it, and ours, can quantum mechanics explain consciousness? Or could we build a conscious AI?
This is the big one, the ultimate debate, and you have some heavy hitters on both sides. On the pro-quantum consciousness side, you have Sir Roger Penrose, a Nobel Prize-winning physicist.
And his argument is that human consciousness does things that a normal computer can't. It's non-computable.
Right. He argues that things like genuine understanding, creativity, flashes of insight, those aren't just algorithms. He thinks they come from quantum processes, actual wave function collapses happening in tiny structures inside our neurons called microtubules.
So our soul, our consciousness, is a quantum effect.
That's his view. But the mainstream view, the anti-side, pushes back hard with that idea we talked about earlier, decoherence.
They say the brain is just too hot, wet, and noisy. Any delicate quantum state would be destroyed almost instantly. It couldn't survive long enough to do any useful thinking.
And if that's true, then even the most advanced AI, like the large language models we have today, are just incredibly sophisticated calculators. They're Turing machines. They can mimic understanding, but they can't have it.
They don't have that non-computable spark.
But the debate is starting to shift a little. You have AI pioneers, people like Geoffrey Hinton, suggesting that maybe these huge models with all their complex feedback loops are starting to develop a kind of subjective experience.
An alien consciousness, one we might not even recognize.
Exactly. But for now, the challenge from the Penrose camp to any AI that claims to be conscious remains. Can you demonstrate true, non-computable understanding? Can you solve the problems posed by Gödel's theorem?
So far, the answer is no. They're still just very, very smart calculators. The jury is out on the soul. All right, let's step back out one last time to the biggest puzzle in the entire cosmos. The fact that apparently 95% of the universe is missing. Let's talk about dark matter.
It's the ultimate inventory problem. When we add up everything we can see, stars, gas, planets, you, me, all of the normal, visible matter.
It's only about 5% of what should be there.
Less than 5%, yeah. About 4.9%. The rest is split between dark matter, which makes up about 27%, and dark energy, which is the other 68%, and it's causing the universe to expand faster and faster.
Our entire visible world is just like the foam on top of the cosmic ocean.
That's a perfect way to put it.
So if we can't see dark matter, how do we know it exists?
Purely from its gravity. We talked of the galaxies. When astronomers measure the speed of stars on the outer edges of a galaxy, they're moving way too fast.
Based on the gravity of the visible stuff alone, they should have just flown off into deep space ages ago.
They absolutely should have. The only thing that explains why they're still in orbit is if there's a huge invisible halo of extra mass surrounding the entire galaxy, holding it all together with its gravity.
The invisible rope.
That's dark matter. It doesn't emit light, it doesn't reflect light, it doesn't block light, it only interacts through gravity.
But here's the problem. We've been looking for a dark matter particle for decades now.
Decades. With these incredibly sensitive detectors buried deep underground to shield them from all other radiation. And we have found nothing. Not a single definitive detection.
And this complete failure to find it has given rise to a challenger theory, right? MOND.
MOND. Modified Newtonian dynamics. The supporters of MOND ask a very simple, very powerful question. What if there is no mysterious, invisible particle? What if our theory of gravity is just wrong?
So MOND suggests that over very large distances, gravity just doesn't weaken as fast as Newton and Einstein predicted.
Exactly. If you just tweak the law of gravity a tiny bit for these galactic scales, the need for dark matter just vanishes. It explains the star rotations perfectly without inventing a new substance.
It's a very elegant solution.
It is, but it has trouble explaining things on even larger scales, like clusters of galaxies. So the consensus is still with dark matter, but the longer we go without finding a particle, the stronger MOND's case gets.
I think of it like this. You come home and find the cake is gone from the fridge, even though the door is locked. Dark matter theory says there must be an invisible cake thief who can walk through walls.
I like this.
MOND says, or maybe the laws of cake physics are different than you thought, and sometimes cakes just disappear on their own.
And just to make things more confusing, the brand new James Webb Space Telescope is finding these huge, fully formed galaxies super early in the universe's history.
And they're too big. They grew too fast to fit our current dark matter models.
The universe is just throwing us curveball after curveball. It's keeping us humble.
I think my brain is now in a superposition of fried and fascinated. That was a lot.
It was. We went through so many paradoxes. Reality is probability until you look. Time can be bent and maybe even flow backwards. And the entire universe is built on these repeating fractal patterns.
You know, the most amazing thing in all of this to me is just us. The fact that we, these big clunky beings stuck in 3 dimensions, can use math and logic to figure out things about realities we can't even perceive. Non-locality, the quantum compass in a bird's eye.
It's a miracle of the human mind. And this isn't just philosophy. This weird physics is why your phone's GPS works. It's why the computer chip inside it works. The strangeness is the foundation of our entire modern world.
Okay, since we've already broken time and space, let's leave our listeners with one last provocative thought to chew on. Let's go back to that idea of time as a 4th dimension.
The block universe.
Right. If time is a dimension just like length, width, and height, then it implies that the past, the present, and the future, they all exist simultaneously. Your entire life from birth to death is a single fixed object, a 4-dimensional film strip.
And if that's true, what does that mean for free will? If the future is already written on that film strip, is our feeling of making choices just an illusion as we experience each frame one by one?
That is something to think about. But before you solve the problem of free will, I recommend you all go observe your dinner before it collapses into the state of eaten by your roommate.
That is solid, practical quantum advice. Thank you so much for joining us on this brain-melting journey into reality itself. Keep asking the hard questions. Keep looking for that missing 95%.
And thanks for listening to Sip and Talk. Make sure you subscribed. And please go check out our good friend Micky's YouTube channel, Micky to Life, for some great memes and travel vlogs. We'll see you next time.